for session 1, and I want to share my screen. There we go. Share. Okay, now you can you see everything that I see? Can you see all your very polite rants? Philip, can you see my screen or not?
Yes, it's starting to share.
Is it starting to share? Okay, so let's just switch to the screen I want you. Can you see my code?
Yes.
Oh, fantastic. All right, so let's just now go there, and I want to try this. Yes, that's going to work. Right, can you see a double screen now with the one that I'm going to use to scribble on and the one for the code?
Yes.
Oh, okay, right, so let's shoot. So let's just set the scene. We are busy, and just before the semester in a previous lifetime, when you still spend time on CRO now, it seems as if you're only spending time on CPB. There was this reaction that we analyzed, and it was equilibrium limited in TAT 4.2. So we could draw our equilibrium line, and I gave you specific inlet conditions, 320 Kelvin. Okay, so let's just 320 Kelvin was the inlet conditions there, and then we saw that the limiting conversion, okay, my line is not perfectly in line, but regardless of what reactor type I use, if I operate adiabatically, I cannot go beyond this equilibrium point, right? So now, let me just change that. If I now asked you to model this, this is not what I wanted. I don't want you to see the memo. Hang on, Jing. There we go for now. This is the one I want to show. Right. So if I now go to my code on the side, let's just make the screen a bit smaller. Hang on. There we go. This is what I asked you to model with the specific inlet temperature of 320. Okay, so I don't know whether you managed that, but we could plot the XA versus volume, and then we can see that there's this initial increase in the rate to a maximum, right? Where I see this inflection point is an indication of increase in the rate, increase in the rate. Remember, the dXA, dx dV is always directly proportional to negative of RA. You can do your mole balance for your plug flow reactor. So over here, we have that inflection point that gives me the maximum in the rate. That's where so the slope is going to increase, reach a maximum, then it's going to drop away suddenly until the equilibrium point where my rate goes to 0 there. Right. So what shall happen if I increase my inlet temperature? So if I increase the inlet temperature here, let's just try a temperature of 350 and see what happens on our figure. So I'm just going to run all there, and if I now look at my figure over there, I can see that I indeed go to a lower equilibrium conversion, and my outlet temperature, right, outlet temperature there is also going to be lower, and I can achieve that in a much smaller reactor, about 30 liters. I can achieve that, right? So if I now should once again include that there, what I've done is I increased my inlet temperature. This is now what happens, is my reactor there goes nowhere, but very fast. So instead of almost 250 liters, it can go to that equilibrium conversion. But I haven't achieved, I can get by with a much smaller reactor, but I can only achieve about 40% conversion because it's equilibrium limited. So now what we want to do is we want to say, all right, let's not limit ourselves to adiabatic operation. Let's say I want to include a utility, so I have I'll just remind myself to change back that temperature over there. I have want to include a utility in my operation. So let's just maybe quickly go through my code so that you can see what I've done here. So this is all the parameters that was given. Either you were given the inlet molar flow rate, you were given Q, it's a liquid phase reaction, you were given all the CP values, you were given the del H and the E values. So using the information for the reference K value at the reference temperature, at 300 Kelvin. Please don't get confused with this reference temperature and the inlet temperature. This is just something that you must practice, and we've practiced this in many of the tests because it's often reported in this format, your Arrhenius parameters. So using that E value, I can calculate a K0, so that I've got a full description of my Arrhenius equation. So this is the information that I am not going to change. We may play around with this inlet temperature value later on once again. So just to get a feel for how warm this is about 47 degrees Celsius. Right, so now this is the information I used in this part of the code. Just to remind myself, T0, I'm going to change that. And for now, I just have the 3 differential equations that I returned from my code. So I need to have initial values for all those inlet conditions of mine. I can calculate the concentration as they are updating. I can calculate an updated K value. Here, I could also, of course, use K0 times NP.exp. And then I have min E divided by R divided by D. So that divide by is my solution for myself not to get confused by brackets. So I follow the order of operations. So that's EXP, right. Okay, so I just use, this is the different ways in which you can calculate the Arrhenius parameter. We also have a Kc value that I updated, and now I can calculate my rate and of course my mole balances for A and B. I could add a mole balance for C. This is not a gas phase reaction, so it's actually not a requirement. If this was a gas phase reaction, and you had to calculate an F total. So if you wanted to calculate an F total, you would have to have FA plus FB plus FC as it updates. Oh, sorry, there wasn't a C in this reaction scheme. Sorry, it's just the A and the B. So on a sideline, apologies, take that back. In many liquid phase reactions, you don't have to model all the components in order to answer the questions that's asked in liquid phase reactions. But in gas phase reactions, you need a mole balance for each of your components because the total molar flow rate must be used to calculate your pressure drop. So if that was now confusing you, remember our reaction is just an isomerization reaction. So A just goes to B. Right, so there, that's comments. A just goes to B. Right. Okay, so now what we want to add is we want to add a utility. So we are going to cool down. So we are cooling down stuff in our plug flow reactor. So we must manipulate our energy balance. So in our energy balance, we now need a term that describes our heat transfer. And in order to do that, we are going to have, if UA, I'm going to have a term for that. It's the utility temperature minus the temperature. Let me just make doubly sure that I've got my brackets correct. Yes, so this is my numerator over there, and my denominator, that is up there. That's fine, everything fixed. But let's now, of course it's going to give me an error, because in order to do that, I need a value for UA. Right, and where am I going to find that? So first off, I'm going to start by choosing a realistic value for the overall heat transfer coefficient. And what I've prepared here is previously, so let's just assume we've got organic solvents. So organic solvents, that is part, that's our reactant. So we've got methanol, or a hexane or a hexene or something like that. So it's organic components, and we want to cool it down, cooled, and the utility we are going to use, and it's an appropriate utility because our inlet temperature is about 47 degrees Celsius. So let's say we are going to use water. So first off, you need to understand what are you going to use in order to bring about heat transfer. And then there are lots of references where you can find typical values. So this is what I Googled, typical overall heat transfer coefficient values. That's what I asked Google to find me. And of course, you will corroborate that by more academically acceptable sources, like looking in your Perry or in Coulson and Richardson, your design textbooks. So what I we don't have a heat exchanger. We have a cooler. Why is it a cooler? Because we are going to use a utility, a typical utility, and we've got organic solvents. That's what I now said. I'm going to look where does my system fit in best, and typical U values for this system. So without the need for me to calculate that in detail, I can see what that value typically must be, right? So now I can actually say, let me choose something, and I am going to choose 400. Let's just see what the units are. Very, very important. Units here, watt per meter squared, Kelvin or degrees Celsius. So let me just make a note for myself here, another note, that this is in watts per meter squared per Kelvin. Right. Okay, so that's going to be confusing. Let's just have it like this, meter squared Kelvin or degrees Celsius. Now I need the A value. And the A value is the heat transfer area that I have in my reactor in meters squared per cubic meter reactor. And we derived a formula for that. We said that is equal to 4 divided by the diameter of my tube. So let me just scribble a bit again. So if I want to, so let's just erase, big eraser. Oh, I can do that. Let's see. Oh, okay. There we go. Sorry about that. Waiting for me to delete. Right. So if I now just want to remind you about what this A term is when we derived it, we said, unless, you can, when you are somewhere in a non-CRO environment, you can choose very weirdly sized reactor shapes. Generally, these plug flow reactors are built as tubes, bigger tubes, smaller tubes. So we've got a cylinder of which we can calculate this circumference. So this is the area where heat transfer is going to take place per volume, and this is then that little volume over there. So we derive that the area per volume, so we had area per volume, is therefore equal to that pi times the diameter divided by pi diameter squared divided by 4, and that is where that area comes from. So it says it's 4 divided by the diameter of my tubes. Okay, remember, so we now encountered the situation that we can have lots of tubes. So we can actually have 1, 2, 3, 4, 5 tubes, each with their own diameter. But you must realize that here the total area will be multiplied by the number of tubes, and the total volume, this is the volume of a tube. This is the area of a tube, the heat transfer area, so it's not the cross-sectional area. If I just multiplied this by the number of tubes to get the total area in my reactor, the number of tubes will cancel out. So I can either have one tube that is very long, and it will give me the same area as 5 tubes that's got the same diameter, but it is shorter. Right. Are you still with me? Just give me a pop, somebody, a thumbs up that I hear you. Am I speaking to myself? Thank you very much. Okay, cool. Right, so there we go. Let me just clear my large eraser. This is fantastic. Okay. So let's now just go back to our code to implement this. So now, of course, it's going to give me an error because I must choose, me personally, the design engineer. It's one of the design decisions I must make, is what is the tube diameter that I'm going to choose. And of course, this is going to impact lots of variables in your reactor. It's going to impact your pressure drop, your heat transfer area, and later on after the recess, you will see it can also impact the degree of mass transfer limitations that we have. So I'm just going to choose a 25 millimeter tube. This is about an inch. And I am not going to choose a crazy tube diameter that I will have to have specifically manufactured for my reactor. You buy tubes for specific material types in certain diameter ranges. So you are limited kind of by the suppliers. If you want to have an Inconel tube or you want a stainless steel 314 stainless steel tube, you are limited by the sizes that are available to buy off the shelf. Okay, so if you want them to specifically roll or manufacture tubes for you, you're going to pay much more. So we chose about 1 inch, and now we can calculate UA. Oops, a daisy. Inch there. So we can now calculate UA. It's simply equal to U times A. But let's now check the units that we have here. We had watt per meter squared Kelvin. This is meter squared per cubic meter. So this will give me, in other words, watts per volume reactor in cubic meters Kelvin. And what is the volume parameter that I'm using in my model currently? I have the volume of my reactor. Let's just put it over here so we can use it. The volume of my reactor, I'm going to choose as a basis 100 liter reactor for today. I've got that in liters. Okay, so now I must fix something here because I want this to be in units of watts per liter Kelvin. Right, watts per liter Kelvin. So now I must realize that I must change that. So in that instance, I need to, okay, there we go. So 1 cubic meter and 1 cubic meter. So I know that 1 cubic meter is equal to 1,000 liters. Right. So if I now have to calculate this, am I correct in saying that I have to divide this by 1,000? Do you agree with me? Just give me a pop if you agree. Okay, so it sounds like it's a read there. So now my units are correct. And of course, now I have to choose a utility temperature. We said we are going to use water. Let's just say this is the inlet temperature of my utility for now. And we've got it available at a realistic temperature of 25 degrees Celsius. So I'm going to use water as my coolant. There we go. Right. So in my energy balance, let's see if we have now defined everything. So what I'm going to add for now is I'm going to say, I want to add a profile of how the utility temperature changes over my reactor. So as soon as I do that, I need to add the TU dV. Okay, and I also need to specify an inlet temperature for my utility. So my inlet temperature I now chose as T0. Okay, so of course my DTU dV, DTU dV, sorry, and this is now for the option where I choose a constant TU is simply going to be equal to 0. Right, so let's run it and we see what is going to happen. So for our, so what I've done here, so sorry, I skipped that part. I wanted to show you this in subplots. I'm not the best plotter in Python. This is my fallback for adding subplots. Is I've got my figure and I am adding for conversion. I want to add a subplot. I want 1 row of plots with 2 columns. And this is going to be my first plot in that. And now I can plot the volume span, and this is my conversion. And I want to add the temperature along the length of my reactor as my second subplot. So once again in the same row, but the second column, a 2-column row, and this is my second plot. So I can now add, let me just add a plot for my utility. So TU plot. And I am going to add a subplot. There it is, subplot. And it is going to be, therefore, now I'm going to have to change stuff because I suddenly have 3 plots. So this is 3-1, 3-1, and this is going to be 3-2. See? 3-2, and there we go. Have I done it correctly? F.add subplot, and I can plot stuff there, and it is, what do I want to plot? My V span, and I have to plot my TU. So let me just see if I unpacked my TU here. Yes, I've got my dense output. No, I forgot about that. So TU is going to be, and I now use the dense output through, so my solution is just going to be integrating that PVR with my volume. Let's just use the volume of my reactor that I can change as a variable. I set it up over there. I'm going to change it as a variable. And now I think I am ready to run. I think I'm ready to run. So let's just see whether I was in fact, yes. Okay, so let's just check our figures. So this is now my utility temperature. Oh my word, I didn't specify. Sorry. The U plot, and I want to set my label. So for X, it is going to be equal to the volume in liters. And the Y label is now going to be equal to the utility temperature, TU, and it is in Kelvin. Let's make this one, yeah, it is blue, so that's fine. There we go. Right. I don't know why it wants to complain and then it changes its mind. So look what I have done by adding this. So in a 100-liter reactor, marvelous, I can achieve an astronomical 2% conversion by cooling stuff down. Right, so it doesn't look good for me. However, what I do notice is, yes, and I can see what is the problem here is that if I consider my rate, I'm not utilizing that initial increase in the rate. So this is just showing a constant decrease in the rate, but at least it's not at equilibrium yet. So let's just see what happens if I really go crazy with my reactor volume. So let's see if I've got a 10,000 volume reactor, what's going to happen? Oh, there we go. And can you see what's happening here? This is now, if you check out what this temperature is there, it goes to the temperature in my reactor is now pretty much the same as my temperature of my utility. And I still have not achieved equilibrium there. I'm still climbing. So let's just add a 0 there. It's very easy to add zeros in code. It's much more expensive to do it in real life. Oh, wow. Okay, so look at this. So I can, if I have a very, very, very large reactor and I cool constantly, I can actually win the equilibrium battle at least. But I am not winning the rate battle there because that is such a terrible, terrible, terribly huge reactor. So let's just go back to our 100-liter reactor. So, okay, so this is for the constant utility temperature, but this is not what's actually happening. In real life, we actually have a change in that utility temperature because it transfers heat between our fluid and in our reactor. So let me just comment that one out, and let's just write one. Oh, that's just horrible. Sorry, I can't leave a spelling mistake once I spot it. Right, so let's have one for our co-current heat exchanger. For a co-current heat exchanger, I have to do an energy balance for the utility over a slice of volume. And Vogler does this. You can go and find this in Vogler on page 500 and 501. You can go and find this equation. But what it basically says is this amount of heat that flows to or from your coolant, this is exactly the same but opposite as what is flowing to my utility. So flowing to my contents in the reactor must flow from my utility. So this is just UA, it's a basic times, and that is TU minus T. So note the negative sign. And now I also have to divide this by the energy carrying capacity, but now it will be the mass flow rate of my utility times the CP value of my utility. Right, so let's just call this, I'm going to have this as a single term, and I'm going to calculate that now outside of my loop, because I must now specify this. I must tell the code, and I must decide as engineer, how much fluid, coolant, am I prepared to have flowing through my heat exchanger, and what's the CP value of that fluid. So I must specify that, and so my mass flow rate, let's just think about that for now. I am going to choose a value of, I practiced this before, so I didn't just randomly chose it. I thought about it and I played around with a few values for my crazy reaction system that I figured gave you to understand. This is in kilograms per second, 5 kilograms per second. This is a lot. This is a lot. Because I always, when I want to get a feeling for how much it is, I always calculated in how many tons do I have to transport per hour. So this is going to give me about 18 tons in an hour. Am I correct? So because it's that times 3,600. So that's 18,000 tons per hour. It's not unrealistic. It's possible to do. But I'm going to have a huge pump. So I'm going to have to pay for that. And I'm going to have a very high pressure drop. High pressure drop over my, my fingers are very cold. High pressure drop over the shell side of my heat exchanger thing. But let's just live with it for now. And my CPU of my utility, that is what I have ordered. And at this stage of your careers, I'm sure you would agree with me, and this is kilojoules per kilogram second. And now I can calculate mu CPU, which is equal to m times CPU. Have I got it correct? Let's just check our units now. So if I have this, I have it in units of kilogram Kelvin. Sorry. If I calculate that, I have it in units of kilowatts per Kelvin. Does it correspond to the unit system I am currently working in? It does not, because I work in watts per liter. So here I converted it. So that's already in watts per liter. My independent variable is liter. So I must make sure that I've got this in the correct units. Right? So therefore, if it's in kilowatts, I need to multiply this by 1,000 for the units to make sense, to give it in units of watt per Kelvin. Does it make sense to you? Give me a pop so that I hear you're still there. Some thumbs ups, please. Okay, thank you very much. Okay, so let's see if it is now going to run. Let's beware the green screen. So that, not no pink screen. All right, so let's see what's happening here. We haven't improved anything by much. We can still see, yes, we've got that very low rate because we've got still pretty much the same kind of conversion. I can at least see that my utility is heating up somewhat. My utility is heating up somewhat through that reactor, so there's nothing wrong with my model. It works. This is still not a very satisfactory kind of reacting system. Right, so I can once again just increase my reactor volume. Okay, so let's say, where were we last? How many zeros did we add? So, okay, so at least I can, in a 20,000 liter reactor, so this is somewhat better. So let's have a 20,000 liter reactor, somewhat better. I can achieve pretty much 100% conversion. Right, so it depends on, okay, in the shape here, of course, I'm going to go to a minimum, and then the reaction, the exothermic nature of the reactor. It's a very large volume that we are integrating over. So we can expect these. If I zoom in to this part of my figure, it will not look as horrible as it's looking now, because I'm plotting it over the entire span of my volume. Right, so still not the best. I think I'm going to not pause here. I'm just going to stop the recording. So this was for the constant utility temperature and the co-current utility flow. And I'm going to see if I can manage to switch screens. Yes.